Okay, so previous set of slides were about the classes with a little bit of mention of patterns. And we talked about the main classes that the concurrency frameworks are built on, which are looper, hidden, message queue, hidden, handler, visible, message runnable, visible, and a few other things like future task and executor, which are largely hidden. Now we're going to kind of talk about the pattern dimension of this stuff. Some of these patterns will be very familiar to you. Other patterns will be newer. And what we're going to be focusing on, of course, in the rest of the course are these patterns and how you use them and so on. So that's what we're going to talk about. We're going to talk about the concurrency frameworks, which exist here in the Android runtime and are used all over the place by the upper-level frameworks and applications, and talk about how they map to various patterns in the literature. So you probably hopefully all know about the Gang of Four book, which is this one. Most of the pattern, and there are patterns from the Gang of Four book used in what we're about to talk about. I think I have at least 3 of them here. There's template method, and factory method, and strategy. And there's a few others lurking around in various places like iterator and so on. But the bulk of the patterns we're going to talk about come from other books. And they typically come from the Pattern-Oriented Software Architecture series, which were written by me and or colleagues at various places. And these patterns, the reason why there's a bunch of them is because they focus primarily on concurrency and communication. Whereas the Gang of Four book, by and large, ignores concurrency and communication almost exclusively. There are a few examples of places where patterns in the Gang of Four book are also useful in concurrent and networked environments, but they're usually as an aid to something, not as a direct thing itself. So that's good. That means there's other things to learn. It's also interesting to note that the people who wrote the Gang of Four book, who were really smart guys, had their focus primarily on understanding user interface frameworks. That's where a lot of their expertise had grown up with when they were writing the book. They had all been doing user interfaces. And at the time, which is back in the late 80s, early 90s, user interfaces were not threaded. Actually, even today, they're largely not threaded, for the reasons we've talked about. So, perhaps it's no surprise, the Gang of Four's situational awareness with respect to concurrency and issues of concurrency was relatively low. And in fact, some of the patterns in the book, like our good friend Singleton, which we'll talk about later, is actually very problematic when used naively in a multi-threaded environment. And we'll talk about some of the subtleties involved with that. OK, so you can find out more about the POSA patterns by looking at the POSA books. So let's talk about some of the patterns. And I'll first talk about the patterns. Some of these will be very familiar to you at this point. And we'll talk about sort of where they appear in Android. And obviously, it appears a lot more places than I'm going to show you. But these are some of the highlight places where it shows up. So one of the patterns, very basic concurrency pattern, is monitor object. As you remember, hopefully, from the discussion of monitor objects when we talked about Java concurrency and synchronization mechanisms, monitor objects basically give you a way to synchronize concurrent method execution, so only one method runs at a time in a particular object. And you can, and that is using synchronized blocks or synchronized statements or the synchronized keyword, whatever you choose. And it's also possible to use notification mechanisms to wait and notify so the threads can coordinate their interactions cooperatively. So those are the 2 main things you get with the monitor object pattern as a pattern. And if you take a look at the POSA 2 book, it explains all this stuff, and it talks about how you have synchronized methods, and only one of them can run at a time, blah, blah, blah. Now, as it turns out, of course, there's lots and lots of different ways to implement this. Android, or rather Java, bakes some of that stuff in to the virtual machine with Java objects, with wait, notify, and notify all. And the synchronized blocks, and the keyword, that's all baked into the language. You can also use Java reentrant lock, Java condition object to do these things yourself. And so, in fact, if you look at Android, you'll find lots of monitor objects using built-in monitor objects, but that's kind of boring. And you'll also find places where they use some of the higher level abstractions from Java util concurrent. One place, which also appears in Java, by the way, is in linked blocking queue. So linked blocking queue uses monitor object. And what's interesting about linked blocking queue is that it actually uses a very interesting form of monitor object that has a pair of locks, not just a single monitor lock. You don't see this very often. It's used because they want it to be able to allow concurrent access to the beginning and the end of a blocking queue, a linked blocking queue, so those things could run in parallel. So they use two locks, a head lock and a tail lock. Kind of interesting. So if we have a chance to talk about the monitor object pattern, I will show you the implementation and show you how all that stuff works. OK. Another pattern that appears in Android as well as Java, but we're talking about Android here, is called thread-specific storage. Let me first see if anybody recognizes the following legacy abstraction. Anybody here know what Erno is? Which is spelled E-R-R-N-O. Erno. Does anybody remember what that is? Did you guys play with that in operating system class? So what do you recall about Erno? What is its purpose in life? Nathan?
It indicates the last error, the last system error.
It indicates the last system error. So you call a read call, read returns -1, saying something went wrong, and Erno is set to whatever went wrong, like file deleted or whatever, you know. OK, so what else do you know about Erno, in addition to the fact it stores the last known value?
Isn't it global to the thread, but it's not available to other threads?
Exactly. Exactly. So Erno looks global, right? In your program, you say Erno equal blah blah, or checking Erno equal blah blah, and it looks like a global variable, but actually, its implementation is thread specific. Why is that? Why does it have to be that way?
Well, I mean, you may not fail on all your cores.
Right. So if one thread were to return -1, and you really use the global variable, it would set Erno to an error, and another thread would come along and clobber it right away, right? So Erno is a great example of thread-specific storage, because it looks global, but in fact it's implemented in a thread-specific way. And that's exactly what the pattern is about. It allows multiple threads to use one logically global access point to retrieve an object that's local to a thread without incurring locking overhead on each object access. So the key things here are, it looks global, but it's actually local, and therefore you don't have to worry about locking it, because there only is one thread at a time that's going to access it. And without getting too far down the weeds into how this actually works under the hood, the way it works under the hood is either there's a data structure in the thread itself. There's a couple of different ways to do this. Let's assume we're doing the efficient way. The thread abstraction keeps some kind of data structure. And so every thread, so here's thread 1, here's thread 2, here's thread 3, and so on. Every thread has a data structure, which is typically an array that can grow. And each thread local object is given an index that each thread uses to index into its thread local array to identify the thread local object that we're referring to. So Erno actually turns into a macro call that goes and looks up in this array and then finds the indexed location that corresponds to the Erno value, and then you can read it very quickly.
Is this
Jake?
very static?
It's typically allocated with the thread itself.
Okay.
So you could imagine it could be allocated dynamically, but if it was, it would only be accessible via the thread.
Right.
Or it could be part of the thread control block. There's many different ways to do it. So that's what thread-specific storage is all about. And Java implements this, and Android picks it up through Java, of course, through the thread local class. So thread local is a class that's used to access thread local objects. And the looper happens to be one of the kinds of things that you can access via thread local storage. So you use thread local storage to store a looper, and then every thread has a looper in the same offset, but each thread's looper is a different looper, if that makes sense. So each thread, thread 1 will have a looper. Thread N will have a looper. They'll all have separate loopers, and they'll all be accessed at the same offset. This is all implementation detail from the internal array that's used as part of the thread control block to manage access to thread local storage. So again, it's the kind of pattern that doesn't get used very much, but when you need it, it really makes your performance better. All right, next pattern. This is a pattern that originally was documented in the POSA 1 book, and then has been rewritten a couple different times, and still, in my mind, isn't quite what it needs to be. And when we redo the Post-it 2 book, we'll probably sneak it in there and revise it to make it more effective. But basically, this is called the command processor pattern. And this pattern packages a piece of application functionality, think Java task, as well as its parameterization as an object, think runnable, right? You know, inheriting or implementing runnable. And it takes this thing and it can be used to execute it in a different context, such as a different point in time, like using a scheduled thread executor, where you put it onto a queue to run at some point in the future, or run it in a different process, or run it in a different thread, etc. So once you've objectified a command as a unit that can be reasoned about and stored and queued and run independently from something else, you can then run it in a different context. So this is the command processor pattern. You can see one of the variants here. And it's used various places in Android. It's used in the HaMeR framework, where you go ahead and you post a runnable, and that stores the runnable in the handler's, the looper for the thread it was going to in the message queue, and then that's turned into a run method call that's dispatched. So that's one way it's used. And we'll talk about that when we talk about the Android handler. And it's also used in another context, very different context, but the same pattern. There's something that's called the intent service. And this is part of Android's inter-process communication framework called the intent framework, or the intents framework. It's very intense. And it allows you to be able to take things that are called intents, which you've looked at very briefly at the beginning of the course. You probably forgot all about it by this point. But you create intents, and you can put intents into, you can pass intents to the intent service, and they are processed by calling the on-handle intent callback hook. So we'll talk more about this when we get to the service portion of Android, which should be coming up very shortly. All right, so those are some other patterns. So command processor pattern rather, thread local storage pattern, monitor object pattern, 3 cool patterns, all POSA patterns. There's other patterns, though. So another pattern is called the active object pattern. So monitor object, think about monitor object. Monitor object is a passive object. The monitor object, when you invoke its method, even though it's a synchronized method, the method implementation steals the thread of control of the calling thread and uses it to execute the method. Now, it may have to, serialize and synchronize and notify and wait and so on, but it's using the thread that called it to do its work. That's what monitor object does. It's a passive object. Active object, in contrast, defines requests on components, objects, for example, as the units of concurrency. So a method request or method call is a unit of concurrency, and these requests can be run in different threads from the thread that invoked the request. So remember, with monitor object, thread that calls is thread that runs. With active object, thread that calls is not the same as the thread that runs. And in fact, you typically have one or more threads running inside the active object, and when clients invoke method calls, they get queued up in this list of pending methods to run, and then they're pulled off one at a time and executed by the active object scheduler. Okay, so thinking about that, where have you guys seen active objects so far? You've actually seen variants of this already. In fact, we talked about it earlier when we were going over the quiz. Well, we'll find it out. First, I'll tell you where it appears in Android. So in Android, the HaMeR framework allows you to be able to send a message from one thread where it is then dispatched on a different object, which is a handler, via the handle message callback. So you send a message in the one thread, and it's dispatched via the handle message call. So that's sort of a variant of active object. There's another variant of this, which is used by Android's inter-process communication mechanism called messengers. And you can send a message, and this then gets sent over here. And there's a whole pile of cool stuff that takes place with the messenger interface. We'll talk about that later as well. And then the third thing, which is what we've already talked about, is the way in which you submit callables to thread pools in the executor framework. So in the executor framework, you can say, as a client, here's a callable, which is a two-way task. You submit the callable, and you get back a future. Depending on how you deal with it is up to you, but you get back a future. And then that callable is enqueued and run in the thread pool in a separate thread of control. So the thread that invokes submit is not the same thread that runs the call method on the callable that was submitted to the executor framework to do its thing in a thread pool. So that's yet another variant of this as well. And the executor framework illustrated the use of an active object in that context. So there are several different variants here. And then the last pattern we're going to talk about here, and when we come back and we start looking at all the code, we'll revisit this stuff and it will sink in a little bit deeper. I just want to give you the overview first. The last pattern is half sync, half async, which is one of the more interesting patterns that is in the Posted 2 book. The purpose of this pattern is to decouple asynchronous and synchronous service processing in a concurrent system by having two intercommunicating layers, one of which processes things synchronously in multiple threads. That's the sync layer. And another processes things asynchronously in a single thread. That's the async layer. And then there's a queue that's used to mediate interactions between the layers. And of course, that's what's used by the async task framework, where you can have the user interface thread invoking operations on the async task framework by calling execute. And under the hood, there is a bunch of processing taking place with a pool, potentially a pool of background threads that run synchronously. And when the results are done, they give the results back to the user interface thread via the onPostExecute hook method, which we'll talk about later, which is a way to get the results back to be processed in an asynchronous, non-blocking manner. So this is a really cool example of that pattern used there. Oh, and then there's one more pattern called broker. Forgot about that. This is really more of an inter-process communication pattern, although you could also use it for concurrency, and it's used for concurrency in Android. And basically, it allows you to invoke what look like method calls on what look like objects. And under the hood, the broker does all the job of getting the request from the caller's address space to the server or receiver's address space. And we'll see how this gets used with inter-process communication and concurrency in Android, although it's really much more of an inter-process communication mechanism. And this is used for the Android binder framework, which we'll talk about later. All right. So just, yeah, Jake.
Is the half async, half sync, is that the executor completion service?
Actually, the executor completion service uses the proactor pattern, which I didn't really cover here because the executor completion service really isn't used that much in Android, although you're welcome to use it, but it's not used as part of Android's concurrency frameworks, but it is definitely cool. And the idea there is you have a bunch of tasks running, and then the completion results are put into a queue that can be run asynchronously with respect to the processing. And that's really more of the proactor pattern. The async task framework uses the half sync, half async pattern. But they end up being very similar in the way that Java and Android uses them. There's also a bunch of gang of 4 patterns that are used. So you all know template method at this point. You have a template method that calls a bunch of primitive operations, which I like to call hook methods. And so that allows you to fix the steps here in one method and then defer to subclasses how to process those steps. And for example, as we'll see later on, the looper, there's something called a handler thread. Android defines something called the handler thread. And it defines a hook method called onLooperPrepared. And that's where you can go ahead and do your thing. And onLooperPrepared will do some stuff here that's called as part of the run method on the handler thread. It calls onLooperPrepared. So that's a hook method. So run method is the template method. onLooperPrepared is the hook method. It can be overridden to do various kinds of things. Strategy. Hopefully if you remember strategy. Strategy allows you to be able to have an algorithm with a sequence of steps, and you can plug and play the implementations of those steps. It's kind of like a more dynamically bound version of template method. And this gets used, as we'll see in much more detail later, with the Android AsyncTask framework, where you can go ahead and set the appropriate type of executor. And when you call execute, then the right thing will take place to process the work. And then finally, factory method. You hopefully remember factory method. You defer to subclasses what kind of object is created. And we already saw an example of this earlier called the thread factory. And the thread factory is used in order to be able to create a new thread without having to change any of the executor framework code. You can provide a new thread factory that will provide the implementation. And that's used in the AsyncTask framework as an example. All right, so to kind of wrap this stuff up, these concurrency mechanisms are used all over the place in Android's concurrency frameworks. But they are the building blocks for the domain-specific frameworks. The stuff that you get with Java out of the box doesn't deal naturally, of course, with the idiosyncrasies of Android, because it wasn't built for Android. It was built to be used in a more generic way. So the Android developers then added these frameworks to be able to do more Android-centric things for what they were trying to do. And there's lots and lots and lots of other patterns. We've talked about other patterns already, but we'll see examples of these things as we go through the slides some more.